Our next exercise in this section deals with the next sort of variety of variation that we see, which is inverse variation. So really quickly, let's read through the question. We say that the time t it takes to drive between two locations varies inversely with the rate r at which the traveler drives. We're then told that the trip takes approximately 20 hours for someone driving a fixed distance at an average rate of 65 miles per hour. We want to write a model for the situation that gives the time needed for a traveler to drive the fixed distance. So what's important here would be first to note that we're dealing with inverse variation. The time varies inversely with the rate. In the notes, you'll see that inverse variation in particular, says that y varies inversely with x if we have something like y equals k over x, where k is again the constant of variation. Now in this case, we are told to use different variables. We have t instead of y, so we would say t varies inversely with r. So instead of x and y, we're going to have r and t respectively. So we'll skip that way of expressing things for now. Now in our second part of the question setup, we are told that it takes approximately 20 hours, so t would be 20 hours, to travel the distance at an average rate of 65 miles per hour. So our rate would be 65 miles per hour. Now, just so we stick with some standard physics notation, I'll get rid of hours and miles per hour. I'll instead call this 20h. And miles per hour means we're talking about miles divided by hours. Okay, so this might get a little bit large, but I like to include the units because at the end of the day we can verify that we did everything right if the quantities we come up with have units that make sense. Alright, so we know time, 20 hours, is equal to k divided by 65 miles per hour. Okay, now if we're interested in solving for k, we want to, and that's what we need in this case to set up our model correctly, we want to multiply 65 miles per hour over to the other side. So we'll end up with k equals 20 hours times 65 miles per hour. Now the nice thing about these units is we see that hours and dividing by hours sort of cancel out, and we end up with k equals 1,300 miles. So then we can set up our model completely. We know that time is equal to the constant of variation, 1,300, in this case miles, divided by the rate, where the rate will be given in miles per hour. Now in the next part we're asked how much time would the traveler save driving the same distance at 80 miles per hour. So we could think to ourselves, well, it takes 20 hours to drive the distance at 65 miles per hour. How long would it take to drive the distance at 80 miles per hour? And our model is going to come in very handy for calculating that. So the time needed to drive the 1,300 miles at 80 miles per hour now this is another case where our units can simplify a little bit. we have 1,300 miles divided by 80 miles per hour. And we can kind of pull the units out to the side and say we have miles from the numerator. And if we flip the unit from the denominator, we have hours over miles. So it's a little funny, but you can work with units just like regular fractions this way. So time should, in fact, be measured in hours, and that's what we're observing. So the time it would take to drive that distance at 80 miles per hour comes out to 16.25. 16.25 hours. Now what that tells us, we're not quite done. We wanted to know how much time would be saved driving that speed, that rate. Well, it took us 20 hours in the first situation. It takes us 16.25 in the second. Let's include our units. So the savings would be 3.75 hours. All right. Now that's a fairly long trip, so going 15 miles an hour faster saves you a pretty significant amount of time. However, if our trip were shorter, that number might be smaller. Okay. Now, referring back to our model, we said that we wanted the independent variable to be the rate. So as we let the rate vary, what happens to t, the time that it takes to make a given trip? That means that when we're labeling our axes here in part C, we want the rate to be the horizontal axis, and we want time to be the vertical axis. Now, if I went back and thought of this equation in terms of the original definition, where we have y equals k over x. Now this has the overall structure of a rational function. This kind of looks like y equals 1 over x, or y equals 2 over x. And we know exactly how to graph that kind of thing. We can plug in additional points. We know we're going to have a vertical asymptote at x equals 0. We know we're going to have a horizontal asymptote at y equals 0. So the overall shape of the graph will look very much like y equals 1 over x. Okay, now we know a few points that should lie on the graph. We know when the rate is 65, the time that it takes to make this trip is 20. So 65, 20, we'll put that right there. And on the other end of the spectrum, if you go 85 miles an hour, so if your rate is faster, your time decreases. So we see that if the rate goes up to 80, it only takes 16.25 hours to make the trip. Now, from this graph, it would imply that if we went slower, it would take longer. And that makes perfect sense, right? Since we have this intuition about velocity, about rate of travel, and time. If you go faster, you're going to get there sooner. If you go slower, you're going to get there later. So this exhibits a rational curve. The shape of this looks like 1 over x. So what that means is no matter how fast you go, right, if you go 10,000 miles per hour, you'd be way over on this end of things, to the right as r increases to infinity. But it's still going to take you some amount of time to travel, to get there. This type of variation, varying inversely, doesn't involve any powers. We'll see another type that does involve powers in the next exercise.